Welcome to 32nd lecture of video course on tribology. Today's topic is very interesting. What we are going to discuss, the friction of rolling element bearing. Why do I say that's interesting? I will describe on the second slide or next slide. In previous lecture we discussed about how to select a proper bearing based on load consideration, based on number of rotation considerations. What is expected life? Is that expected life with 30,000 hours, 40,000 hours, 50,000 hours? We can select the bearing accordingly. Now we come to the interesting part. We say the friction in anti-friction bearing. The name itself is quite interesting thing. We are talking about anti-friction bearing. What is the meaning of that? Is that there is no friction or negative friction. A bearing which can resist or show there will not be any friction in bearings. Just opposite of the friction, and we are going to discuss about the friction in that anti-friction bearing. In number of books it has been referred anti-friction bearing. That's why again and again I am using the word anti-friction bearing. But in a true sense, in a tribology sense, these bearings are not anti-friction bearings. They are rolling element bearings, show lesser friction compared to sliding friction, particularly the start condition, not even in a running condition. Sliding bearings show much better performance during running condition if there is a proper lubrication. However, we call anti-friction bearing or rolling element bearing as anti-friction bearing. The reason behind is these bearings show more or less same coefficient of friction under static condition and kinetic conditions. There are not much variation in coefficient of friction during running condition. So it's much more stable. It shows a much better performance. When I think from a power consumption point of view, whatever the power consumption, maybe 1000 RPM, slightly more than that, by and large it will remain same or it is much more stable. Now, what are the causes of friction in rolling element bearing? One obvious cause we can think about is hysteresis losses. The hysteresis losses generally happen when there is a loading and unloading of any mechanical element, and that is shown here. In this case, you can see there is a graph in epsilon and sigma. Sigma is representing the stress, sigma is representing the strain, and is a general way to find how much deflection will occur during the loading condition and unloading condition. What is been shown here, as the stress level is increasing, the strain is also increasing initially. To some extent there is some sort of non-linearity in this, but when it is unloaded, I am just showing this line. When first the loading is happening, there is no deflection for certain duration and a certain value of sigma. After this getting loaded and deflection starts and strain starts, it reaches to max value. After that we are reducing the stress. When you are reducing the stress, we are able to find out the some sort of the loop. It is not a perfectly elastic. Obviously, the some energy is getting lost. If the loop area is 0, then energy conservation happens. Obviously, that 100% energy is returning back to the system. But whenever there is a loop like this, that means there is some consumption of energy, and some consumption of energy means there is some sort of friction in mechanical elements. That's why we say there is a elastic hysteresis in rolling element bearings, when the one rolling element is getting pressed against the other rolling element, or is getting pressed against races. Interesting thing is that the coefficient of friction, particularly for elastic hysteresis, is very low, particularly for some good material. We are discussing about the chrome steel, which has been commonly used in ball bearings. Now, this figure shows load is being applied and maximum load will occur at this ball. I am assuming this is a ball bearing, there is an inner ring, there is an outer ring, this arrow is showing a force direction. and this force direction when is loading the ball. After a certain rotation, obviously it's a few degree rotation, this ball will be shifted to this side. If I am assuming the clockwise rotation, ball will be shifted to this side and other ball will come into picture. That means there is still a distribution of the load on this in between two balls, but load will decrease on this red ball and load will increase on this ball. That means there is a continuous variation of the load on the ball. This is happening over here. When we are increasing the stresses, that means there is a more and more load being applied, and more load means more and more deflection. That can be represented as something like that. We are assuming that there is no load initially. This is a green color bar is there. Now, if I am applying a load on this, assuming a slight load, not a significantly high value, but finite value, certain, let me say, whatever the load carrying capacity of the bearing, and I am just giving a 10% or 12% of that. So, in that situation, this yellow color line will appear, and this is showing a deflection line. If we increase the load, we are able to see another orange color line over here. Further increase in the load, we are able to see this red color line. I purposefully selected these three colors because this is a yellow color ball. Initially, there is a green. That means there is no load on the rolling element. Then yellow color line shows some load and some deflection. Then orange color line over here that shows a higher deflection compared to yellow color line, obviously the deflection which is causing, which is experienced by this rolling element. Deflection in this case will be more than this. And finally is a maximum load over here. That's the red color. And as this rotation starts, from red color it will shift to the orange color, from orange color it will shift to the yellow color, and finally it will come to the green color. That means there is a continuous loading and there is a continuous unloading of one rolling element. That is, if the material is not good, then there will be more bigger loop available, or there will be larger energy loss for that material or for that bearing. So the hysteresis losses will be higher if we choose some cast iron, if we choose some other material where the energy loss is higher. While in the case of chrome steel, which has been used in the rolling element bearing, that has a lesser coefficient of friction. And if I show only the one curve, we say that we want a steel such a manner, if it is loaded in direction, it should return back on the same path. There should not be any area available in this curve. Loading and unloading should be giving the same curve. If we are getting same curve, that means there is a lesser or almost negligible hysteresis losses, and that is shown over here 0.0001 coefficient of friction, particularly hysteresis condition or for this kind of a reason. However, when we write coefficient of friction, basic assumption behind this coefficient of friction is that friction force is proportional to the applied load. If applied load is a P on an element, the friction force will be proportional to this. But it has been experienced. They have a curvature, and this deflection is not proportional, it is slightly more than proportional. That means this coefficient of friction cannot be directly multiplied with the P to get the results in true sense. And this shows of a ball bearing, this power is a 4/3. For the rolling for roller bearing, there is a larger length and the deflection will be slightly more non-linear curve, and will be getting P slightly or higher power of that. However, this is more on a research site, and we should investigate whenever we record accurate results. But when we think about the comparable results or comparison among the results, comparison among the bearing, and when we are thinking the friction as one of the criteria of the bearing selection, then we may not we may neglect this relation. We say that okay, F is proportional to P. It is not a, or we say the power is assumed to be 1. It is not a 4/3, it's not a 5/3. For time being, we are assuming the F is proportional to P for our calculation purposes. So this has been discussed elastic hysteresis and rolling elements. The second one is the sliding. Even though there is a rolling element bearing name, but in those bearings sliding occurs. There will be some sort of relative velocity, there will be some sort of tangential velocity, and that will not be rolling. This there are a number of reasons we say that in rolling elements we know there will be cage to keep separation between the rolling elements, to keep separation between the balls, to keep separation between the rollers, and that separation occurs with some sort of a contact on the rolling element, and there is no rolling action out there. Even though there is a touch but the rolling action will not be there, it will be more like a sliding action. Similarly, there is an inner ring, and we know that to support this to some extent axial load, we use some sort of a curvature, and again that is causing a slight change this side, a slight change that side is going to introduce some sort of a sliding. In pure rolling cases, in pure radial load, there may not be any sliding, but we know there will be some sort of axial force, it will be shifting, and then pure rolling action will not be there, some sort of sliding will occur. And last one is in this sliding case is the seals. We use seals to prevent oil leakage, to prevent grease leakage. So if we are using the seals, then what we are sacrificing, that's the friction. So with the seals, coefficient of friction will increase, the overall coefficient of friction will increase. It will not be the same as without seals. So sliding is caused by the ring and ball interface, particularly when there is other load, other direction load. In this case, we are talking of the radial bearing, and we will say that if there is axial load, then there is more sliding. When there will be any cage, naturally there will be some sort of sliding between the cage and rolling element. Then comes the seal, there will be a sliding because we are able to see there is a contact. We are assuming this is the elastomer, this is embedded in outer ring and is touched with the inner ring with some sort of pressure, maybe the spring tension or maybe its own stiffness, spring whatever the seal material we are using that has a stiffness. So it will be resisting leakage of oil, but that resistance is going to introduce a sliding between the seal material and inner ring, and that is going to cause friction, or that is going to cause energy loss. So that is a sliding. Now to reduce the sliding, we often use a lubricant. It's an interesting thing that lubricant otherwise is not required. If there is a pure rolling action, there will not be any contact, also that there should not be much area contact, so we do not require any lubricant in this situation. But to reduce the sliding as well as to reduce the deflection of the surface, to reduce the seizure of the two surfaces, we use lubricants. That will be detailed, or that will be discussed in detail what kind of lubricant will be proper for rolling element bearing, but for time being we are discussing about the friction in anti-friction bearing. So we say that there will be some sort of lubricant sharing. Reason being, there is a relative motion. If there is no relative motion, we don't require any bearing. We require a bearing to provide a relative motion, and if there is a relative motion, surely there will be sharing of lubricant if we are using some lubricant. Easiest way to incorporate lubricant sharing is Newtonian law. We say that Newtonian law says that shear stress developed in the fluid is proportional to the viscosity and velocity gradient. Velocity gradient, we are assuming that Z has Z is along the radial direction, and there is some gap between the rolling element and the inner ring. It's something like this. There is a rolling element or a rollers or the ball, and this is the inner ring or outer ring. Particularly in this case, when there is getting in this form, it will be inner ring, and there is a lubricant. When the rolling element, this rolling element comes closer to this and also rotate about its own axis, naturally what it will do, it will try to drag this lubricant in the space. The dragging action itself is going to cause some friction, is going to lose some energy. And further, this is having some velocity, inner ring will be having different velocity. So there will be a difference in velocity of rolling element and the inner ring. naturally that will cause a shearing of the lubricant, and that is what we are trying to predict. We are trying to estimate, we are trying to find how much energy loss will occur because of the lubricant. And the last one is the seals. Of course, we mentioned in sliding the seal component, but it has been experienced. A seal, almost if there is a seal, it can show very high friction, even more than 30% friction just because of the seals. And if there is a misalignment, then the coefficient of friction due to seals will increase even more than 50% of total friction. That's why they have kept this seals in a separate category. Sliding is generally with in presence of the lubricant, it will change. That's why we go ahead with the three different components. We say that friction due to the loading and unloading, or due to the load. We say load dependent component of the friction. Second, we simply say lubricant and sliding component of the friction. If we are keeping this together, we know very well the lubricant is going to reduce the sliding, or it will reduce the friction between two surfaces, and lubricant itself is going to cause friction, or is going to cause a friction. Naturally, it need to be a combination. That's why we consider lubricant and sliding, or lubricant and velocity components separately, load dependent components separately, and seal dependent components separately. And we can say if there is a misalignment, every component will get affected. But that will create, we said that will require slightly more understanding, more analysis, the detailed analysis, and in this course we are not going to discuss that in detail. We will be touching little bit upon the misalignment, but not to a very great extent. We will show some sort of elementary analysis to show the what is the effect of the misalignment, but not a detailed analysis. However, we can say if we consider these four components of the friction, we can say total friction will be because of friction due to the load, friction due to the speed, and friction due to the seals. Here when we are talking the speed, we say the speed and the lubricant, that will be better word, the friction due to the speed and lubricant, a combination. So we will see how to estimate friction due to load, how to estimate friction due to speed and lubricant or lubrication, and how to estimate friction due to seals. We will be using some sort of empirical formulas, not a complete scientific finding, but has been done, a number of experiments have been done, because there is a lot of nonlinear relationship in this, and if we try to do a detailed analysis, it will take complete one course on that. Let's take a first component, which is the load dependent friction movement. Again, we are using the friction movement. We are not talking about the friction force, because it's the rolling action, and whenever there is a rolling action, generally we use the word movement instead of using the friction force. So we need to calculate what is the friction movement due to the load component. Say it will be proportional to the applied load. We are not taking non-linearity due to the ball geometry, due to roller geometry. We are just taking proportional. That means this is still an approximation, not to a very good level, but it gives a feel of the friction, gives a results of the friction. We can give a good comparison. Obviously, it can be a basis of good comparison. Then there is a coefficient of friction, and this is a radius. What is the radius of the more like a torque arm or moment arm. And when we are talking about the force P, we are assuming there is an external load. In addition, there is a possibility of preload. What is the meaning of preload? We say in bearing, if there is no clearance or there is a negative clearance, then there will be some load initiated or developed within a bearing that will be different than external load. How this kind of load will be generated? Generally, when we mount bearing on the shaft or in some housing, and if there is an interference fit, that interference fit will reduce the clearance, or we say that it negate the clearance between the rolling element and inner ring. And there is a negative clearance between the rolling element and inner ring. Naturally, there will be load, or there will be deformation of those rolling elements as well as the inner ring. If there is a deformation initially before applying external load on that, that is called a preload, or that will be causing preload on the bearing. and many times the preload is more than 5 to 6 times compared to external load. That's why we say the mounting of bearing is one of the important steps. If we are designing good bearing, we are selecting good bearing, but we don't know how to mount this bearing properly, it may lead to failure of bearing within a few hours of operation, even though we are designing bearing for the 1000 or plus number of hours, but bearing may fail within a few hours. So this is first component of the friction. We say that friction due to the applied load. There is a coefficient of friction, applied load, and torque arm. Again, this P may be resultant of axial force and the radial force. It is not individual. So that's why we say that P can be represented as Fr, the radial load applied, and axial load applied, or maybe axial load because of some sort of a sampling or coming from some other components. Interesting thing is that we are not calculating equivalent load in this case. We are just finding the resultant load. Reason being, we are concentrating only on the friction. We are not talking of the load carrying capacity. And load carrying capacity, that will more involvement is required, more detailed analysis required. That's why we go ahead with the equivalent load. While in this case, we just take P as a resultant of Fr and Fa, the radial load and axial load. Now, we can calculate P from a problem itself. We can calculate D, or we can estimate D from the data given to us, but coefficient of friction will be different, will be depending on the geometry, and generally given by the manufacturer, or can be figured out or can be digged out from manufacturing catalogs. That is, one table is given. Again, this is not a complete table, or it's not a D table. If manufacturer is different, then table may be different. So always we should rely on the manufacturing data provided by the manufacturer compared to this kind of thing. But this gives some sort of the feel of coefficient of friction. We can think, okay, yeah, this bearing is going to show much higher friction compared to second bearing. So we don't worry about absolute values of this coefficient of friction, but relative value will be more or less same for all manufacturers. So the deep groove ball bearing, where there is a slightly lesser flexibility for the rolling element, coefficient of friction is on the higher side. While self-aligning, there is a more flexibility, coefficient of friction is slightly lesser. Same thing happens with a cylindrical roller bearing, slight more flexibility, coefficient of friction is a lesser compared to deep groove ball bearing. Coming to the needle roller bearing, there is a lesser flexibility. That's why coefficient of friction is on the higher side. And whenever we talk about the thrust bearing generally have higher coefficient of friction compared to radial bearings. That is key factor. Wherever we find the thrust bearing, we find that the coefficient of friction is more than the radial bearing. We can use this data provided applied load is just 10%, because these loaders data have been generated for the 10% of load, which is that 10% of dynamic capacity, when the applied load, or which is the applied resultant load, is or the equivalent load is almost 10% of dynamic load. The load is more, load is lesser, than this friction force or coefficient of friction will vary. Particularly whenever the load is a much higher side, say equivalent load P is more than 10% of the dynamic load carrying capacity, this friction force or this component of friction or the coefficient of friction will be much higher than this stated value or listed value. Then the second component is a lubricant and speed dependent component. In previous slide we discussed about friction force due to the load. While here in this case we are talking about the friction force due to lubricant and speed dependent, which is depending on the speed and lubricant. That is generally represented with the ML. M is a movement, L is lubricant dependence. It has some steady and unsteady value. Say value is lesser than 2000, which is the product of kinematic viscosity and RPM, rotational speed, is lesser than 2000. This coefficient of friction or this friction movement will be steady. It's not going to change with the speed, it's not going to change with the viscosity. By and large, value is a constant, except it depends on the FL parameter, which is again depending on the bearing type or geometry. So FL or geometry type, and particularly when we are talking about kind of the lubrication mechanism, it depends on lubrication mechanism as well as the bearing geometry. Now when this product, kinematic viscosity and the RPM is more than 2000 or equivalent to 2000, we have a different relation. An interesting thing is that if I substitute nu into n equal to 2000 in this relation, I'll be getting this relation. So there is a continuity, there is a compatibility between these two equations. Now in this case, whenever we substitute value of kinematic viscosity and rotating speed or rotational speed, we will be able to see that friction force increases with viscosity. If we are using thicker oil, it will cause more friction. If you are using high speed, it will cause more friction. But if this product is lesser than 2000, is not going to cost extra force. It will be by and large the same steady value of the friction movement due to the lubricant and speed. Now finding the value of FL, again we have a number of tables available in the catalogs and even in the books on the rolling element bearing. We can figure out, we can find out, we can use that value of FL. For present lecture, I am using these values only. You can see for deep groove ball bearing, this value is ranging between 0.75 to 2. Question comes, what is the meaning of 0.75 and what is the value of the 2? Why this range has been given? Whenever we talk about the light duty bearing, when the diameter is smaller, when the width is smaller, then we will choose a lower value. When we talk about extreme size of this deep groove, the largest size of the outer diameter and width, then we'll take higher value too. So this range has been given for the light and heavy seaters, or with the dimension are changing. For larger dimension, larger value. For smaller dimension, smaller value. And we are able to see in the case of the grease, a oil spot, oil path, and particularly the vertical shaft. The reason of a high value in this column, high value of FL in this column is because of the difficulty in lubrication. We will not be able to give sufficient lubricant for the bearing lubrication purpose. That's why FL is generally higher value whenever there is a vertical shaft and is supported on bearing, because we know that due to gravity, lubricant will drip away, will move towards a downward direction, and we need to re-lubricate it continuously, or we require a continuous lubrication. And in this case, none of a single lubrication mechanism is showing a continuous lubrication of the rolling element bearing. Says the oil spot, will be some, maybe say after some certain duration there will be oil sprayed on the bearing. In this case, oil is completely in a bath, so there will be some sort of heat generation that will be there also, and it's very difficult to maintain an oil bath, particularly for vertical shaft. That will not be useful, or that kind of bearing arrangement will not be very useful. So in that situation, we require a higher value of FL. Obviously, it is going to cost high energy loss. Vertical shafts are generally going to cost high energy loss compared to the horizontal shaft. So as far as possible, we should go ahead with the horizontal arrangement of shaft. If you are designing some machine, we should give more emphasis on the horizontal shaft compared to the vertical shaft. Here we are able to see there is a change in bearing. If there is a change in a bearing, there is a change in FL value for that. Like in this case, deep groove ball bearing is angular contact bearing, and for angular contact bearing, you are able to see the higher value of FL. As in this is going to give us, it's going to cause a higher friction compared to the deep groove ball bearing, whether it's the case of the grease, even in the case of the oil spot, even in the case of the oil bath, even in the case of vertical shaft. In all the cases, angular contact bearing is going to cost more, particularly from friction point of view. We studied in previous lecture, angular contact bearing has a high dynamic load carrying capacity, and it is going to survive for more number of operation or service life of angular contact bearing will be more than the deep groove ball bearing. Now, if we consider the friction also as one of the objective function, then we may say, okay, in some cases angular contact ball bearing is going to give a better result. In some cases the deep groove ball bearing is going to give us better results. So it will turn out to be the what is the main aim of that bearing. Is it a more support or is a lesser friction? Whichever is more dominating, we choose a bearing accordingly. Interesting thing is similar kind of comparison can be made in a cylindrical roller and needle roller bearings. So when cylindrical roller bearing is used, we know there will be a lesser number of rollers, and when you are talking about the needle roller bearing, there will be more number of rollers. When there are more number of rollers, naturally the dimension, the load carrying capacity will increase for the same dimension. And if you want to retain the same load carrying capacity, dimension of the needles rollers will decrease, and that is going to save the space, and that is a main advantage of the needle roller bearing. Needle roller bearings are required whenever there is a space constraint in radial direction. However, this is going to cause a friction. We are able to save space, but we are going to lose energy. See, so a cylindrical roller bearing, this FL factor is 0.621. 0.6 for the light series, 1 is for the heavy series or higher side series. However, the needle roller bearing FL is a 12. That means it is going to cause a 12 times high friction compared to the cylindrical roller bearing when there is a grease lubrication. Coming to the oil case, the difference is not that much significant. Here the needle roller bearing are more comfortable with the oil lubrication mechanism. These are the 6 times. Again, these are based on the experiments, and there's maybe there will be some change if we shift from one catalog to other catalog. Coming to the vertical shaft, needle bearing should not be used, which is going to again cause a higher side, very high friction moment for the needle roller bearing is almost 24 times, or is that 6 times compared to the cylindrical bearing, or FL is at 24 in this situation. So based on this data, we can find out what will be the friction moment due to the lubricant and speed. Last in this series is a seal dependent friction moment. Again, in this case, there are 2 components. One is a fixed. If the geometry is fixed, this is fixed. Other case, it depends on the geometry also, which depends on the diameter also. So, in the deep groove ball bearing with the 10 mm, 20 mm, 30 mm, 40 mm, 50 mm, 60 mm, 70 mm, 80 mm, F2 remains constant. That is remaining 10 Newton mm. However, as the geometry increases, we say that value of diameters are increasing, this factor is going to get domination. Let's take a minimum diameter as a 10 mm of the bearing. Naturally, outer diameter will be around 20 mm. So 10 plus 20 is 30 and divide by 20. So it is a 1.5 and 1.5 is square of that. That means going to add to this. Now if I increase diameter, assume it is 20 mm and this may be a 35 mm or 34 mm. So 20 plus 34 is 54 divided by 2. So this factor is increasing with the dimension. That means it has 2 components. One is exclusively depending on the kind of bearings which we are using. Other depends on the kind of bearing as well as dimensions. So based on this formula, we can find out what will be the friction moment due to seals. Again, in this case, basic assumption is that seals are provided at both the sides. There is a possibility the friction is seal is provided only on one side. In that case, this moment will be reduced to 50%. The seal is only one side, friction moment will be reduced to 50%. Now, if I know MP, if I know ML, if I know MS, I will be able to find out what is the total friction moment. That will be simply a summation of MP plus ML plus MS. To understand the various factors involved in this kind of calculation, let's take one example. We say that estimate. Again, we are using the word estimate because there are a number of assumptions lying in our theory and our calculations. So we cannot say calculate friction moment. That's an estimation. Calculation means I'm 100% successful in my theory, and I'm 100% confident about my relations, 100% confident about the results which I'm going to get. However, in this case, we are talking about estimation because we are not 100% confident. So, estimate friction moment of a bearing, that is 6214. This is a deep groove ball bearing. 14 is a 70 mm diameter. If I multiply 14 with a 5, I'll be getting 70 mm. It has seals at the both the end. That's why we are writing 2RS1. If it is only 1 RS, then the seal is only one side. If it is RZ, then we can say the seal on one side and a shield on other side. All configurations are available in the market. We can choose a bearing from a catalog as per our requirement. However, in this problem, we are talking about the seals at the both sides. That means we are going to use the MS, full value of MS. We are not going to reduce to 50%. If it is only RS, then we will be reducing to 50%. Now, in this case, again we are saying the bearing is running at the 6000 RPM. That means the ring is rotating under 5000 Newton load or 5 kilonewton radial load. There is some sort of lubrication mechanism described out here. We say the when jet lubricated. It's more like an oil spots. We have some sort of compressed gas, and we push oil with the compressed gas, and only that some sort of droplets will come out. There will be jet formation, and we are using a synthetic ester jet oil, which has a viscosity of 6 centistoke, or in talk about the MKS unit, we say mm square per unit second. At operating temperature. What is operating temperature? We are not describing this. Whatever the operating temperature, it has a viscosity equal to 6 centistoke. This word is important over here because we know as operating temperature changes, viscosity will change. It will not be same at the starting, or it will not be same as the room temperature. There is a possibility of high heat generation in bearings, and that will change the lubricant temperature. Now, how to do calculation for this? We say, okay, we require dimensions from the bearing catalog, and this is already given. 14 mm is going to be a 70 mm. 14 series is going to make a bore diameter of 70. 5 into 14 is a 70 mm. Max diameter for this series, a 6214, is 125 mm diameter. So, based on these two dimensions, I can find out what will be the mean diameter, which will be required particularly for calculating or for estimating friction due to lubricant and velocity. Now, for the first component, load dependent component, we require coefficient of friction. For the deep groove ball bearing, because we know the 6214 is a deep groove ball bearing. Now, we utilize this coefficient of friction into a radial load, which is given as 5000 Newton, and bore diameter, which is that is the momentum. Momentum can be calculated as 70 mm divided by 2, that is 35 mm. Now, using this substitute this value 0.0015 into 5000 into 35 mm, we will get a moment value as a 262.5 Newton mm moment value. So, this is the first component, which is based on the load, and the bearing geometry has been calculated or has been estimated. Second component requires the product value, product of kinematic viscosity and operating kinematic viscosity and operating speed. Kinematic viscosity in present case is a 6 centistoke, and the rotational speed in this case is a 6000. So, 6 into 6000 makes a 36,000. Which is a greater than 2000. Naturally, we need to use a first relation. For first relation, we require dm, and that is a dm in this case is 70 plus 125 divided by 2, the mean diameter, and that turned out to be 97.5 mm. The mean diameter is known now for us. New and product is known to us. We can directly use a relation which we described in the previous slides. That's angle. Friction movement due to lubrication is 10⁻⁻⁷ into FL into nu into n to the power of the 2 by 3, and this is a heavy component, is a highly sensitive component. The dm we are using power 3, right? So 10 to minus 7. FL in this case is equal to 1 because of the jet lubrication mechanism, and this product is turning out to be more than is a 36,000, which is more than 2,000. That's why we are using this relation, and dm is a 97.5 and is a cubic, so we are using cube of that. This overall is turning out to be 101 Newton mm. It's not as high as what we have calculated for the load dependent component. So in this case, friction moment is not very high, maybe say around 40% of the load dependent component. The third component is a seal, because we are using 2RS1, and the seal is on both the sides. And for the deep groove ball bearing, for deep groove ball bearing, F1 is given as a 20 and F2 is given as 10. We will be utilizing this. So 10 will be substituted here. That means whatever the dimension, 10 Newton meter, 10 Newton mm will be the friction moment. Plus, depends on dimension. We know minimum diameter is 70. Maximum diameter is 125. F1, which can be figured out from this table, as a 20. And if we do the calculation, it turns out to be friction due to seals is 105 Newton mm. Now we can add up all these moments, and this is turning out to be 468.5 Newton mm. To get a feel of energy, to get a feel of power loss due to this bearing, we can think about the rotational speed of the bearing, which is maybe assuming in this case 2000, which was given earlier. In this case 6000. Rotational speed is given as 6000 rpm. Now if we use a 6000 rpm, then will be a lot of friction loss. Now if I assume friction loss, or maybe operating speed can be reduced to a slightly lesser level, 1200 rpm, even in this case there is a cost of the 59 watts. If I assume the 6000 rpm, it will be 59th watt into 5. So roughly 300 watt we are going to lose in this bearing, which is significant. Almost half of the HP, or slightly lesser than half HP, is going to be lost in a bearing. That's a significantly high friction loss in the bearing. And if we try to calculate based on only 1200 rpm, this movement, obviously that the coefficient of friction is turned out to be 0.0027. Now, why we are doing this? To differentiate whatever the friction moment, coefficient of friction given in bearing catalog for the load dependent component, it was only 0.0015. While when we are doing here, we are finding that coefficient of friction is going on higher side. That is turning out to be 0.0027. Now, even if I go ahead with the 6000 rpm, then multiply with the 5 in the numerator and then divide by 5 again in denominator, 5 will cancel out. Coefficient of friction still will remain 0.0027. So this coefficient of friction should be counted compared to coefficient of friction what we get from the catalog, that is a load dependent component, or that will be utilized only for load dependent components. This is just 2 times of that coefficient of friction. Many times we say this coefficient of friction is negligible. We should not be worried about too much about this. Even the coefficient of friction about 0.01 is not a very high value. That's a tolerable, and it will always happen. We cannot improve bearing further. So there's no need to worry. As a possibility, we can keep that in our mind. If the coefficient of friction is lesser, or is 0.01, we should not worry about the bearing. Then bearing selection should be exclusively based on the load and speed on we say that operating hours. However, there's an interesting point is that we need to find out if there's this much energy is generated, this much power loss is happening in the bearing, what's going to be the temperature of the bearing, because the bearing temperature also will change. Changing the bearing temperature, there's a possibility of change in clearance, there is possibility of extra preload on the bearing. Those need to be considered properly. So to think about that, we can think about the temperature. However, there's one exclamation mark comes over here, so okay. this is a loss in a bearing. Okay, and if we talk about the 6000, the 5 times of that, this is a higher side. So almost 295 watt have been lost in the bearing, and still we are saying this bearing as an anti-friction bearing. So we need to think whether should we call anti-friction this kind of bearing anytime anti-friction, or we should not be calling this. We should call only on the rolling element bearing. I prefer to call this as a rolling element bearing compared to anti-friction bearing. Now, as I mentioned, if there is a heat generation, naturally there is a possibility of some sort of temperature increase of the bearing surfaces, and if there is a temperature increase is significant, then what will happen? There is a possibility of change in the dimension, and if there is a change in dimension, there is a possibility of loss of the clearance. There is a more possibility of interference rate among the rolling element and the rings, and if there is an interference rate, then it will cause a more load. More load is going to cause more temperature. More temperature is going to cause more load. So it will be more like catastrophic value. That's why the many times bearing fail instantaneously if they are not properly mounted, if there's a friction is not controlled properly, if the temperature is not controlled properly. So we say that in this case, what we need to find out what is operating temperature. Ideally, operating temperature should be within a few degrees, or we say the increase in the temperature should be within few degrees, or slightly more than the atmospheric temperature. However, to find out that, what we require how much heat is generated, how much heat has been dissipated, or we require a balance between the heat generation and the heat dissipation, or we say that heat convected or conducted away to some other elements. That's why we require heat dissipation rate and heat generation rate. That should be in equilibrium. If that is in equilibrium, temperature will be more like within tolerance. If there is a more heat generation compared to heat dissipation rate, then naturally temperature rise will be very high. There will be always energy balance, but this is continuously going to change if heat generation is going to continuously increase. Let's take a simple case. We say that we know how to find out the heat generation rate. Using the previous slide calculation, find out the MP, find out the ML, find out the MS, sum up, find out what will be the operating speed, multiply with that, and we will be able to figure out how much heat was generated or what is the power heat generation rate. Coming to the heat dissipation, we can make some sort of assumption. So if we know ambient temperature, what we are looking for the temperature increase, temperature difference. For that purpose, what we require is something like how much heat can be dissipated from the surface. That means we require more or less surface dimensions. We require the length, we require the peripheral dimension, which is that circumference of the rolling elements. And in addition, we require heat flow density, which is generally given by manufacturer from their material property point of view, their arrangement point of view. And in addition, if there is a cooling arrangement, if there is a possibility of the fan running near bearing, temperature will be different. So we require a cooling factor, we require a density factor, we require dimensions. And there is a relation, again this is what we say the empirical relation. We say that bearing can dissipate up to 20,000 watt per meter square, provided dimension, the mean diameter and the length of the bearing is lesser than 4,000, which happens in most of the small size bearings. But if dimension is increasing, is going beyond this, going beyond 4,000 or equivalent to 4,000, then we should use this relation. You can see we substitute value of the 4,000 over here. The numerator and denominator both will be 4,000. That means that this ratio is 1, and we'll be getting same result as this. However, if dimension is increasing, I should be happy if the dimension is increasing, the surface area is increasing, but it's not happening. Surface area is increasing, but heat dissipation density is coming down. We know that the material is not able to dissipate that much heat. So overall not very encouragement or a lot of encouragement to increase the dimensions. For larger dimension, this density will be lesser compared to what we are getting here, 20,000. Now we say the maximum value of density is 20,000 watt per meter square. Right. Now if I know QLB, that is the heat density, and if I know the temperature, ambient temperature, this is the cooling factor. We said that for normal cooling, natural cooling, and we are not using any constraint, we are not restricting bearing from all the sides, then this factor will be equal to 1. If we are using extra force cooling, we are using some sort of fan over there, then this cooling factor will be on slightly higher side. That means more heat dissipation is possible from the bearing surfaces. However, there is a possibility, there is no circulation, there is no air circulation, and then the environment also remains on slightly hotter side. Heat dissipation is not that much fast. So this factor can be treated as a 0.5. Again, these are based on empirical relation factors. We can say that we will not be getting accurate result, we will be getting a feel of the temperature rise. Now minimum diameter can be figured out, maximum diameter for the bearing geometry will be known to us, length will be known to us if the bearing geometry is given, angular speed is operating speed will be known to us, movement or friction movement due to load, due to the lubricant, due to the seals can be estimated. So we will use this relation to find out what will be the operating temperature, this T. If operating temperature is within a few degrees, we do not have to worry too much. Now if we utilize this relation for the given bearing geometries, we will be able to estimate what will be the operating temperature. That is given, we say that previous example whatever been mentioned, let's add few more data to find out what will be the operating temperature. So in this case, assume the ambient temperature or T ambient is a 30 degrees centigrade and natural cooling of the bearing is naturally cooled. That means factor is equal to 1. OD as was already mentioned, that is a 125 mm, value of the B is a 24 mm. Now we require these data. Rate of heat generation we already found in a previous slide, previous slide, that was a 468.5 Newton mm. If I divide by 1000, it will turn out to be Newton meter per second. This is given as 2 pi n and is a rotational speed as a 6000 in this case. When we find the rate of heat generation is turning out to be 294.4 watts. Now we required this dimension for heat dissipation, and we say that this dm into B is 70 plus 125 divided by 2 into 24, that is turning out to be 2340, which is lesser than 4000. That's why I say that for most of the bearings this product will be lesser than 4000, and that is there. That's why we can use directly heat dissipation density as a 20,000. This is the ambient temperature. KT is in this case of 1, minimum diameter is known, maximum diameter is known. Value of the B is also known to us. We already figured out and estimated this value omega into amp, that is turning out to be 294.4 watts. If we do calculation estimate, we find the temperature is 30, which is ambient temperature, plus 1 degree. That is well within limit. There is not a much problem. We can choose this kind of bearing from a friction point of view. It's not going to cost much loss or much energy loss. It's not going to change the bearing dimension significantly. In this case, 1 degree temperature rise. As a tolerable, we can go ahead with this. But there's a possibility. There's a possibility if there is some sort of a misalignment, then there is a problem that may increase the temperature significantly. We'll be studying or we'll be discussing those aspects in our next lecture. Thank you. Thank you for attention.